Are we good?
No, we don't have 100% yet.
Talk to me. What are you talking about 100%? Those are grams.
Yeah, but that is percent.
No. Yeah, that was those problems in Chapter 7 when we could change a percent directly to a gram. All right, now just for giggles, even though the problem did not ask for this, tell me how I would calculate how much oxygen I used. Has someone got a bright idea on that?
Add up the products and minus the pentane.
Okay, so here's what this guy wants to do. He wants to use something called the law of the conservation of mass, and it says this, that if you add up an entire side of a chemical equation, let's call that the right-handed side, all the masses, that all the masses over here must equal whatever that number is. Okay? That's what the law of the conservation of matter says. It says the matter just can't be randomly created and destroyed in a chemical process like this. So 54.4 plus 26.7. Now that means the entire right-hand side weighs 81.1 grams. That means the left-hand side must be 81.1 grams, right? So how much does the oxygen weigh? Minus 17.8. Just like he says, get rid of the pentane for a total of 63.3 grams. Okay. So here's what we got. We have something that's kind of like gasoline. If you want to know what it smells like, what it would look like, kind of like gasoline. We've put a little bit here. We've put 17.8 grams. We've lit it. Here comes a flame. We would have used exactly 63.3 grams of oxygen from this room, and we would spit out 54.4 grams of CO2 and 26.7 grams of water, vapor. And then that flame would be burned out. This is a way to quantify it. Now, what if you use Joe King's method to calculate that? So let's start from what? What do you start from? The Levantine reagent, right? 17.8 grams of C5H12. What's the first step? Convert to moles, right? Because chemists love the moles. Well, we've already did that 3 times. 72 grams of C5H12 per 1 mole of C5H12. Okay. Now talk to me about the ratio between pentane and oxygen. 1 to 8, Bella says. Okay, so 1 mole of C5H12 to 8 moles of O2. All right. Now, 1 mole of oxygen weighs how much? No. How much does a mole of O2 weigh? 32. 16 and 16, right? 32. All right, so 17.8 divided by 72 times 8 times 32. That's all right. You guys are still my favorite class, right? Okay, so what is this right here? This is 63.3. Do you get that? Now, should this answer and this answer jive? Sure they should. All right? Because, see, I can't have a method that works, and he have a method, and then, you know, that ain't going to work. Everything's got to work exactly equal. Now, let me ask you this. What if, Bonnie, we did this? 26.7 grams of water. Okay, so I'm starting from water, right? Okay, how much CO2 could we produce? Well, there's 18 grams of water per 1 mole, right? All right, now what's my ratio between water and CO2?
How do you know how many grams of water?
Periodic table, 16 plus 2 is 18. All right, what's my ratio, Bonnie, between CO2 and water? I'm going to put you on the spot. CO2, water. 5 and 6. There we go. All right. So here's what we got. We got 5. Wait a minute. We got 6 moles of water Now do you see why I put that water on the bottom? To 5 moles of CO2. Now 1 mole of CO2 weighs 44 grams. Right, because 16 plus 16 plus 12, 44. So 44 times 5 divided by 6 divided by 18 times 26.7. Now what should I get? 54.4. Do I? Sure. Now you may say, wait a minute. This number right here is not the limiting reagent. Are you saying that? Sure. Where did that number come from? Here. Where did that number come from? The limiting reagent. Here's what I told you. I said that all calculations must have started from the limiting reagent. It did 10 steps ago, but it started from there. And then that's why you could go through all this menagerie. What's the point of the story? No matter what information you're given in an equation, you can calculate everything else to an exact detail. All right? Now what we are calculating in all of these numbers here are what are called the theoretical yields. All right? Now you have to understand that what a theoretical yield is pencil and paper and calculator. This is the most you could get in the world based on the laws of physics and so forth. This is the most you could produce. All right? Now what do you think about practice? Do you think you're ever going to get those numbers exactly that high? Very rarely. Sometimes you do. All right? But a lot of times these numbers are going to be lower. All right? For a couple of different reasons. One is you're a human being. You're going to screw up. That's just life. All right? The second reason is sometimes there are side reactions that go on that you don't know about. So it's actually using this pentane and using this oxygen to make other things that you ain't measuring. All right? So most of the time, the actual, they call those actual yields, the actual yields will be a bit smaller than the theoretical perfect world yields. Are we happy? Wonderful. All right. Do you guys want to work one? Sure you do. All right. Okay, how much aluminum chloride could be produced, okay, from 89.3 grams of aluminum with hydrochloric acid. All right. So before we turn the camera off, let me just reiterate this for just a second. I want to know how much aluminum chloride I could produce, right? Just the theoretical amount from 89.3 grams of aluminum reacting with hydrochloric acid. All right, so give it a go.